Hey everyone, it's David Townsend joining you for another Biz and Bytes session. Apologies that I've been away for a few weeks. As some of you may know, I started a new position at Juniper Networks. I've got promoted to senior sales engineer. Great. But for the last few weeks, understandably, with any new role, there's been time to get on board, enable, take in all the new information there has been. Hence, I've been off for a few weeks. But I've not forgotten what we are here for. I've not forgotten about these Biz and Bytes sessions. And what we're going to be covering during this session is OSPF, Open Shortest Path First Networking LSAs, the link state advertisements. As I said on the last video that I've done all those weeks ago, what we're going to be covering is more detail into these LSA types, types 1, 2, 3, 4, 5, and eventually LSA type 7 as well. And what we're going to be going into is what are these LSAs? What function do they do? Why are they really needed? And really building together all this detailed building blocks so you can understand how OSPF uses these, how they contribute to that link state database and really enable that routing protocol to advertise who's connected to who. So let's get going on this Biz and Bytes LSA deep dive into type 1 and type 2 LSA packets. And so this is the network that we are essentially going to move towards. We aren't going to go into this and show it really during this session because this is a little bit more technical, it's a little bit more advanced. What I'm specifically referring to here are these what we call OSPF special networks, these network types: stub, totally stubby, not so stubby, and totally not so stubby. And the reason why I want to do a deep dive into those OSPF LSA packets first is because once you understand what these LSAs are, what they do, what they show, how they contribute to building that LSDB, that link state database, then you've really got that pivotal and important information to understand, right, for each one of these special networks, what OSPF LSA packets should you see in each type of network? What ones should you not see? And that's important because some of these areas will allow some OSPF LSAs to be advertised into and out of them, and others will do completely opposite in terms of what they will advertise and allow into a specific area and advertise out of another area. But we'll build on that, as I said. First, here comes the OSPF deep dive into LSA 1 and 2. Okay, everyone, so let's get started. So as I said, we're going to do a deep dive on the LSA packets 1 and 2. And this is the network that we're actually going to be using to build up towards that more complex network and those different types of OSPF network types of stub, not so stubby, etc. Now, this might look, depending on your experience, you know, like it's complicated anyway, but don't worry, all we're going to be focusing on here is area 0. We're not going to be concentrating on area 1 or 2, completely forget them for the time being. For the LSA type packet types 1 and 2, we're only looking at area 0. A lot of our time we're going to be spending on router 1 or R1, which is 1.1.1.1 for its router ID. Guess what? The R2 has up here, which is the ABR, the area border router between area 0 and area 1. That has the router ID of 2.2.2.2. And R3 down here has the router ID of 3.3.3.3, and that is again an ABR between area 0 and area 2. Okay, so let's get started. So what is the OSPF packet type 1? Let me just turn off the fading marker down here. I've been playing about with this a little bit, so I've learned how to use this pen marker. Hopefully I'll do it justice. But first off, this is what's known as the router LSA, or just router really. And there's three things really that every router in an area is going to send to one each other. So R1 is going to send router LSAs to R2. It's going to send the same or duplicate LSA type 1s, router LSAs, to R3. And guess what? Because they are in the same area, they are going to be sending, R3 is going to be sending its router LSA to R1. R2 is going to be sending its router LSA to R1. So the big point there is that these are only in the same area. Okay, these are not transmitted from one area to another area. So LSA types 1 and 2 stay within the same area. And ABR, where it would be R2, R3 here, it will not take R1's router LSA and then transmit that into area 2. And R2 will not take R1's or even R3's router LSA and transmit that into area 1. It's just not going to happen. So router LSAs always stay in the same area. And there's three things that I said that you will always see in a router LSA. First is the cost. Now, this is other known as the metric in the OSPF world. So it's really the cost to get to an interface. So here, this might have a cost of 1. This would have a cost of 1. This, because they're giggies, would have a cost of 1. This would have a cost of 1. And when these routers in the same area have exchanged their router LSA packets to one another, when R3 learns of R2's 10.0.0.2/30 interface, it is able to see, well, actually the cost to get from this interface over to the router on this interface here, it's +1 here, plus another 1 here, and altogether that's then a cost of 2, because I've got to go from here over to here, and then from here over to here. So it's always adding up the outgoing interface. It's not the outgoing interface and then the ingress interface. It's always the outgoing interface cost that's advertised by the neighbor adjacency routers that you built an adjacency with. So cost, what is the cost to get to the destination itself? The other two values you will always see in a router LSA is what's called the network ID. Okay, and linked to this, a subnet as well. So here, what you're going to see when we configure this in just a second on R1, it's going to advertise the network 10.0.0.0 because I've configured it as a /30. The .0 is just the network ID for that 10.0.0.1 and .2 on the adjacent end. And the subnet mask, because I've defined it as a /30 here, that's then going to be 255.255.255, and finally 252. So that is always advertised for every interface that is advertising to OSPF per router into the same area. So if we take that one step further, if R1 has got another interface here and another interface here, it's going to build another router LSA packet for this interface here and for this interface here. So if you've got 5, 6, 7, doesn't matter how many interfaces that you're advertising into OSPF, that router is going to build that 5, 6, 7, 8, 9, 10 router LSAs to advertise to all the other neighbors in the same area that is built an adjacency with. Okay, so let's take this onto the configuration. So over here, I've got, okay, so here is the R1. So as you can see, I've just gave it the host name R1, so referring to 1.1.1.1 here. And right now there's no configuration on this R1. So if I do edit protocols OSPF and do show, there is absolutely nothing here. What I do have as well, though, if I do top show interfaces gigi 0.0.0, we can see that I've configured the gigi 0 and the gigi 1 interfaces with the obviously the appropriate and correct IP addresses. And now let's just actually start configuring a little bit of OSPF. So now if I just do set area 0, of course, interface gigi 0.0.0/0, don't have to give the unit or the sub interface address or identifier, but by default Junos would create it to a .0 anyway, but it's good practice. If I suddenly do set here, let's just do a show so you could see it. I've now said, well, I want area 0 and I want the interface gigi 0.0 to be advertised to become part of area 0 itself. Now, with Junos, you know that you then have to do commit, ideally a commit check first, but I know obviously that's going to pass. So I'm just going to run a commit, and now you can see it's obviously completed. Now, how do we actually view the link state database or LSDB in the Junos world? Well, I'm in configure mode, so if I just do run, show OSPF database, then I can now see that router 1.1.1.1 i R1, the router I'm currently configuring has advertised a router LSA. But this is just a brief, it's just a summary of the OSPF database. So if I wanted to see a little bit more into that OSPF packet, that router LSA, I do show OSPF database router detail, and let's just do LSA ID. So I want to say coming from here. And now I can see that there is this stub network, the ID, the subnet mask, and the cost. Note the importance here. As I was saying, for every interface per router in the same area that is advertised into OSPF, the routing protocol, it will show the cost, the metric. So here we're saying router 1 is saying, well, to get to myself, to get to 1.1.1.1, which is its router router ID, it's going to cost 1 to get to myself. Why is it 0? It's because that's not a loopback interface. If it was a loopback interface, that would be 0. The network. So again, we got the ID here and the subnet mask. Now, I actually do, let's just go up a bit, and if I do set and this is one I've configured before, loopback 0.0.0, and if I just do just to show you a top show interfaces loopback 0.0.0 or O.0, I can now see that IP address I've given to loopback 0 unit 0 192.168.0.1/32. And if I now commit that, and again, once that's been committed into the running configuration of Junos, I will then run the same command, run show OSPF database. And note now, nothing's really changed apart from the checksum has changed and the age. If I go back up here, before I committed it, you can see the age was 12, suddenly it's 5. That's because there's been an update into this, into OSPF. The router R1 has added an interface into its LSDB. And so now if I do a run show OSPF database router detail LSA ID and now you can see there's the 2 links that are being advertised by myself. So I've got the 10.0.0.0, that's again the network ID. I've got the 192.168.0.1, it's again the ID /32//30. This is a stub, this is a stub, cost of 0, cost of 1. Everything, as I said, that you would need to see to build the LSDB, you're already seeing here. So really the functionality of the router LSA is to advertise to other routers who's connected to me. What are their network IDs? What's their subnet mask? And from my perspective, what is the cost to get to that network via that interface? And then when that adjacency router sees that router LSA, it will build its LSDB and say, okay, network 192.168.0.1 is connected to R1. Its cost to get there is 0, but my cost to get to R1 is 1. So 1 plus 0 is 1. So the cost for me, from R2, R3's perspective, to get to 192.168.0.1 would be 1 in that aspect. Okay, so let's just take this router LSA a little bit further, shall we? So what you could see here is these different types: type stub, type stub. Okay, what does this actually mean? Why is it relevant to the router LSA? Well, there's actually 4 different types of values that you can get from the type. You can see here they're all labeled as 3. There's 4 different types of values that you can get within the router LSA. The last one, which I'll just mention it quickly, is the virtual. This is when you have a virtual link. I'm not going to go through it, but say a company has been acquired by another company. It happens all the time, and both companies are using OSPF, but their networks aren't combined, they aren't converged, and you have completely discontiguous area 0 as the backbone. What you'd have in that aspect is, say over here is that new company that's been acquired, their area 0 over here. What you do is you then create a virtual tunnel to go through, in this case, area 2 to area 0 over here to create that contiguous network. But it's not a permanent solution. It's very temporary. You're much better using some kind of tunneling protocol like GRE, and then sorting out the network infrastructure and architecture as you move forward. That's as much as I'm going to talk about that. One of the values, though, number 1, is point to point. So this is when you define a specific interface type for OSPF. What we're going to do here in just a minute, we're actually going to define a point-to-point network between R1 and R2. The other value, which you could see, is transit. So a transit is when you basically have these routers R1, R2, R3 connected together, and they're going to elect who's the DR designated router, who's the backup designated router, and who are, of course, those DR others, as I mentioned in the previous video, i.e. designated router other, droppers, however you want to pronounce it. The third one is, as we've really seen here, that stub network itself. So here we can see stub to this router ID, to this loopback interface. For both ones, the IDs, the network ID, the subnet mask, and the cost. And you're going to be seeing that same information for the point-to-point, for the transit as well. But really, the difference being is when we have this transit, you're going to see some information actually not being fully present there, but via another LSA type, i.e. type 2, where that information is then actually shown. Okay. So let's move on. So if I come back to set interface, set area 0, interface big 000, interface type, and if I actually push question mark, now you can see the different types of interface types that you can get for OSPF: non-broadcast, multi-access, point-to-point, and point-to-point. So we're going to do configure it as a point-to-point to face R2. I commit this. I'm not going to do any passwords or anything like that, and that will then be committed. But I do not have the configuration at all set on R2. So if I just move it up here, so let me move it over here just so it doesn't get too confusing with the background. There we go. So R2. If I do edit protocols OSPF, show, there's nothing there. So let's do set area 0, interface gigi 0, and it's gigi 1.0, interface type, point-to-point, and let's commit this. Then that will then build the adjacency, hopefully, to R1. Okay, so if I now just do a run, show OSPF, neighbor brief, we can now see already that neighbor adjacency has been built to the full adjacency, i.e. they've exchanged LSAs, whatever those LSAs might be, between one another. Okay, so let's go back to R1, because as I said, that's going to be the focus of today. So if I do run show OSPF database, and now we can see 2 different, here you can actually see the 2 different OSPF router LSAs. So for area 0, R1 has got one router LSA from itself, built into its LSDB. It is now, because I've built the adjacency, seen a router LSA from R2, advertised by R2. The age, 35. The age over here was 38. So there was a 3-second delay for me going from one COI to another COI. And note, even if I was to go into it, even the checksum would be the same itself. So if I actually do run show OSPF database, and if I do the same on here just quickly, we can actually see that the checksum itself is the same between these two different router LSAs. Again, the LSDB is synchronized. It is the same from one router to another area if they are in the same area. If you break the LSDB, then OSPF is not going to work. Okay, so let's come back over here. Now, if I now do a run show OSPF database router, we want to look at the router LSA and do detail LSA ID 2.2.2.2. I can now see all the networks and what's configured on R2. So R2 is saying here to 1.1.1.1 myself, data 10 to this interface with 10.0.0.0.2. It's a point-to-point link, and it's costing me 1 to get there. So cost of 1, the egress interface going out. I can also see the 10.0.0.0, so the network ID with a /30 is a stub network type 3, cost of 1. So let's actually revert this back now. So let's remove the point to point, because in a few minutes I'm going to bring R3 into it. So let's just do delete area 0 interface gigi interface type point to point. I'm going to commit that. If I come back to R2, if I actually just watch the run show OSPF neighbor, that will now be being torn down. You can see it's trying to establish that connection. It's starting to. It's not really going to get there. If I do it again, it's not going to get to the full state, because here it's saying, well, I'm not point to point. R2 saying I am point to point, and they're never really going to build that adjacency. So now if I do delete on R2, delete area 0 interface interface type point to point, and commit that as well, then once that has been passed through the checks, etc. on Junos, if I do the same now, it is now gone to the two-way, and eventually we'll see this going up to the full state. Okay, so it took a bit longer than I expected, but it's now in the full state, as you can see. Right. So let's go back to R1 and see, well, how has that changed? So now if I do a run show OSPF database, nothing's really going to be different on here, except you can now see the network. So the network, let me just turn on my pen. The network is where we start building on the type 2 LSA. And this is what's known as the network LSA. Okay, so what happens in the network with the network LSA is it's advertised by the designated router when you've got a multi-access network like we've got here, who is connected to me. What is the cost? What is the net ID? And what is the subnet as well? The reason why it does that is because if I now do a run show OSPF database router detail LSID 2.2.2.2, we can now see that it's actually lost one of those one of those entries that were in there. If I go back up just a bit, we can actually see here for the same entry, we've actually got 3 networks. If I scroll down, we've only got now 2. Why is that? Well, because I configured one as a point-to-point. We've still got our point-to-point to the router ID, to the from the router ID to this particular interface itself with this subnet mask. But then it's also configured another one saying, well, actually, this network between R1 and R2 is a bidirectional link with a cost of 1. It is a point-to-point. That has been removed now. And instead of having that entry where we actually said about, well, this network here is actually a stub, what it's now saying is actually this network is now a transit network itself. So if I now do set area 0 interface biggie but it's now do 1.0, and we'll commit that. And if I come back to, or if I actually move across to R3, just down here, and I'll move that up. And if I now just do set protocols OSPF area 0 interface gigi, checking I get the right one, and commit this, then what we'll see eventually in just a few seconds time is if I do a run show OSPF neighbor brief, we can now see that the adjacency is starting to build between R1 and R3. So if I do that again, hopefully it's now come to the full state. Still working through the process, it'll take a few more seconds. Now, the default process of a designated router election is, as per previous videos, is first they're going to use and see, well, who's got the highest value here in terms of designated router priority. By default, Junos, every single router will have a default priority of 128. So this will have 128, this will have 128, this will have 128. So there's going to be a tie. The second thing they look at as a tiebreaker is, well, who's got the highest router ID? In this case, it's going to be R3, 3.3.3.3. So let me just see if the neighbor adjacency has been built, and you can see it's now up and running. I do not know what happened there. So let's do, once again, run show OSPF database. Let's just see that information. Now I can see that there is 2 networks for the for this one area. So we got one for the 10.0.0.2 here, and one for 10.0.0.6 here. So let's just do one show OSPF database network detail LSA ID 10.0.0.6 from R3. And now we can actually see attached to R3 is, of course, R3 itself. We can see the router. R1 is attached to this as well. We can see the subnet mask. We can see that 10.0.0/.6 has been advertised by R3. Sequence age, etc. And we can now see the 2 transit links, the type 3s that are being advertised by, in this case, R3 itself. So we can see that attached to me is 1.1.1.1. It's bidirectional, cost of 0, and 3.3.3.3 bidirectional, again, a cost of 0. Okay. So some of you at this point might be wondering, well, hang on, Dave, you said here that, and you said before that actually in a multi-access network, you're only going to have one designated router and one backup designated router. Essentially one network LSA, type 2 LSA for an entire area. But here we could see for area 0 that there are 2 network LSAs. There are 2 type 2 network LSAs, I should say. Why is that? Well, it's actually because, you know, this isn't a fully meshed network. So we've not built an adjacency from here over to here. This isn't a switch. We actually have different subnets here. One in a .0, one in a .4. As such, this is being recognized in Junos as having one network, both in area 0 and one network over here. So here we're seeing one network LSA from 10.0.0.0.6, i.e. from R3. And over here we're seeing another network LSA from R2, 2.2.2.2. So essentially this is saying, well, actually for this link here, I am the DR and you are the BDR. So R2 is the DR, and R1 would be the BDR on this link. And from here, what we're seeing is another network LSA on this link where R3 is saying, I'm the BDR, R1, you are the backup designated router as well. So that's why you are seeing two types of type 2 LSAs in the Junos link state database. Obviously you can change this, but for time purposes I'm not going to. But if I just carry on and do run show OSPF database network detail LSA ID 2.2.2, no, that's the advertising router, 10.0.0.6, so from R3, I can now see into more detail into that type 2 LSA. I can see who's attached. I can see the ID. I can see the cost as well. Where do you get the subnet information from? Again, this comes back to over here. This comes back to the R1. So if I do the OSPF database again, and if I now do, well, let's do run show OSPF database router detail LSA ID 3.3.3.3 from R3. I can now see for the link containing going to 3.3.3.3 for network with interface 10.0.0.6. If I scroll down, I can then see 10.0.0/.6 is a type transit 2, it's not point to point, default metric of 1. And up here, I can see the subnet mask up here. So again, it is a /30. So here you basically see the type 1s and type 2 LSAs working together. The router LSA is really important. It's really the building blocks of that LSDB in a complete area. And again, it is shared from one router to another router to all the other routers in the same area. And as you add interfaces and take interfaces away, causing a topology change, those LSAs, that router LSA is updated throughout the entire area to keep that link state database in sync. And that type 2 LSA builds off that router LSA. It says, well, okay, I've got a multi-access network here, and I'm going to have a designated router. I'm also going to have a backup designated router. Depending on your configuration, you might have one network LSA, ideally, or you might have two network LSAs, etc. And then in the network LSAs, you can see who is attached to this particular network. So on this particular network here, obviously it is point to point at the end of the day. I can see 3.3.3.3, R3 and 1.1.1.1. R1 is attached to this, and the type, so they're both transits, they're not point to point, and they both have bidirectional communication with, and from R1's perspective, cost of 0 using the R2, using the type 2 LSA to get to those. Okay, so that summarizes a bit more detail in the OSPF link state advertisement packets type 1 and type 2. Hopefully you found that useful, and stay tuned for the next video next week. We'll go into more detail into OSPF LSA type 3, i.e. the summary LSA, and there you'll see what happens to that type 1 and type 2 LSAs when we go from one area to another area. What do we use? And that's where the type 3 really comes into it. So thanks for watching, and stay tuned for next week. Thank you. Goodbye.